Hello and welcome to this presentation in which we look at a load on a brake pedal in a Formula SAE open wheel race car. We'll have a fixed joint between a pedal and an arm. We'll inspect a mesh. We'll have a boundary condition. We'll put in a force, and we'll do it two different ways. In load step 1 it's centered, spread evenly. In the second it's off center. We'll review results. We'll move the result of a first structural run into an eigenvalue buckling analysis to see if we have a good factor of safety. We'll consider that we got a negative load factor and look at the buckling load with a positive load, not the negative one. And we'll do it with the off-center load from step 2. Let's go in and have a look at the model, but first, in the project schematic, you'll note that we're going to do a static structural run. And then, just to be cautious, we'll do an eigenvalue buckling analysis in order to ensure that we have a good factor of safety on buckling of the structure. Let's go have a look at the model. Here's our geometry. Two bodies, and the details of how they're bolted together have not been provided in the geometry. But what we're going to do is have a fixed joint tying these two things together so that they act as if you had one body without going into the complications of many faces in contact. So you can see that in this joint we have two red faces involved in the reference side and two blue faces in there involved in the mobile side of the joint. And this has been set right here to be a fixed joint body to body, so the parts will move together. It's a simple way to get them to work with one another. Let's zoom back out. As for meshing, we did a bit of face meshing in order to get a cleaner layout of elements. Did a little bit of face sizing to keep elements of a tolerable size. So there's our mesh. It'll give us a first order look at what the stresses are in this structure. In our analysis, we have two load steps. Here's the reason for this. First off, we've simply fixed the face down here, and we're going to put a load on this pedal and see what stresses result. So it's sort of a cantilevered structure. We have a force, which is spread out over this face. You can see that the angle has it perpendicular to this pedal or pedal face. In the first load step, we're bringing that load up to 2,000 newtons. This is an estimate of the biggest load a person could put on there, and the load's been multiplied by 1.5 to get a bit of a factor of safety. So this is one of those approaches where the factor of safety will be built into the load rather than in the material allowable, where we'll probably look at yield. So there's a force. In the first load step, it's on. The second load step, it's gone again. Then a second load, remote force. Now let me turn on random colors, make that thing easier to see. We have a remote force. It's pushing in the same direction. It's been moved off-center. The z-coordinate has been shifted over to make it off-center. On top of that, a pinball radius has been defined, set to 15 millimeters, so the force is exerted only over this small region. That's going to put a bit of torsion in this structure. We wanted to see if that would produce a worse result when this too has been set to 2,000 newtons. The load might be off-center if a person's foot was off-center when they pushed on the pedal. So note that it's on in the second load step. So with two load steps, we evaluate two different kinds of load on the model. It's a simple linear model, no nonlinear contacts, no nonlinear material properties, and the deflection is small enough we don't need to go into large displacement analysis. So there's our mesh. There were just over 100,000 nodes, so a bit over 300,000 degrees of freedom in this 3D model. Let's go see some results. There's a deformation, and you can see a ghost image of the undeflected model. Here the load is centered, and if I animate this plot, you can see that in the first load step it's pushed straight down. In the second load step, the off-center load puts a twist into it. Here's the state of stresses. Now this state of stresses is being shown at the end of load step 1. You can see time 1 right here. Let's animate this as well. The pedal's pushed down in the first load step and you can see it twisting. And you can see that the stresses are peaking near the end of the second load step. To get a bit more insight as to what's happening, here's a maximum principal stress. Things are going to be in tension. Now what might make this buckle is a minimum principal stress. So you can see down in the bottom of this thing, because we've pushed here and fixed it here, we're getting compression in the lower flange of this. It's almost like a wide flanged beam. So that compressive stress might produce some buckling. And if we look at it at the end of the second load step, notice we were down to minus 126, that's megapascals. And at the second load step, we're down to minus 206. So we're getting more compressive stress when we have that load off center. So we moved on and linked the static structural run to an eigenvalue buckling run. We're considering the last load step, in other words, the load is off center, expecting that that's the worst case. And we've looked for 3 modes. We've not bothered to prevent negative load multipliers. So when we solve this thing, what do we find? The first of the load multipliers has a minus sign in front, implying that if the load was pulling up instead of pushing on the pedal, we would get buckling. But that's not what we're going to do. The foot is only going to push on here, so we want to look at the second mode of buckling. Again, that's based on an off-center load. Let's line this model up about here and see how that thing deforms in the first mode of buckling where we're compressing the pedal off-center. Let's animate that. So you can see that the buckling is a matter of the thing twisting. Not a simple kind of buckling, but you may know from experience that with some things, when you push on them to the point that you get elastic buckling, they do in fact move away in a torsion-like manner. And with a higher load factor, we're still getting a twisting-like deformation. But with that load multiplier being over 37, linear elastic buckling is not going to be a problem in this model. And with a highest equivalent stress that's up around 217 megapascals, ordinary steels will tolerate this level of stress also. So there's a quick review of a model in which we meshed geometry of a brake pedal, joined 2 parts together with a fixed joint, so there are no degrees of freedom involved, and we evaluated the state of stresses with that 2000 Newton load. Thank you for joining me.